You already understand braking. Push a pedal, pads clamp down, the vehicle slows. Now, set that understanding aside, because aboard a bullet train, the mechanism you are picturing is nearly irrelevant to how the machine actually comes to rest. That is a literal statement, not a flourish. Those friction discs bolted to a Shinkansen, the pads squeezing against steel rotors, the exact hardware your mind reaches for the moment somebody says the word brake, sit idle through almost the entire deceleration. They wake up at the very end. By the point they are doing anything you would call work, the train has already shed the overwhelming bulk of its speed and is barely moving. The difficult part of the job is over before those pads ever make contact. So what is doing the difficult part? Hold on to that question, because the answer runs against every instinct you have about how moving things are stopped. Bringing a bullet train to rest turns out to have almost nothing in common with braking as you know it. It is instead a coordinated handover between four entirely separate technologies, each one built for a narrow band of speed, each one surrendering control at the precise instant a different system becomes the better tool for the job. Not one of them is powerful enough alone. Remove any single link and the sequence collapses. And the order they fire in is not a matter of preference. It is dictated by physics, and the physics changes as the speed falls. Why is friction ruled out at the top of the deceleration? Why does the whole procedure have to begin 3 or 4 miles before the platform is even in sight? Why does a system that never physically touches the track generate more retarding force than steel clamped onto steel? And why does one of those four technologies get switched off completely in the one situation where you would most want it working? Let us start with the failure that forced all of this into existence. Here is where most people's mental model quietly falls apart. Push a fingertip down into a bar of chocolate left too long on a sunny windowsill. Soft, effortless, leaves a dent. Now put that same fingertip, using exactly the same force, against the underside of a pan that has been on the burner for 10 minutes. Identical pressure, wildly different outcome. What changed was not the strength of the push. What changed was the heat generated the instant the two surfaces met. Now scale that up. A 16-car Shinkansen set weighs around 715 tons, which is a shade over 1.5 million pounds. And on the Sanyo line it runs at 300 kilometers per hour, close to 190 miles per hour. Those two numbers together describe an amount of stored motion that human intuition simply cannot hold. Every one of those pounds is carrying energy, and energy does not politely disappear when you ask it to. It has to be moved somewhere else. Friction braking has exactly one destination available to it, and that destination is heat. Try to dump all of that into brake pads gripping the wheels, and you are not looking at accelerated wear. You are looking at a thermal event. The energy released would be enough to bring a backyard swimming pool to a rolling boil twice over inside a single minute. The wheels would not decelerate. They would come apart because the steel would pass the temperature at which it can hold its own shape. The pads would not thin out gradually. They would go liquid. Rotors would warp before they glowed, and once a rotor warps, it stops making even contact, which means the heat concentrates into a smaller patch, which makes the warping worse. The failure feeds itself. There is a second problem stacked on top of the first. Brake pads lose grip as they heat. The friction coefficient of the composite material falls once it passes a certain temperature, which engineers call fade. And it is the reason a heavy lorry loses braking power partway down a long mountain descent. So the harder the pads are worked, the less capable they become at exactly the moment you need them most. On a train this heavy, fade would arrive within seconds. Ordinary brakes come up short on a bullet train for reasons that have nothing to do with being undersized. They fail because no material on this planet can absorb that quantity of energy as heat and remain intact. A better alloy will not save it. A larger disc will not save it. The physics closes the door and locks it. So the engineers stopped fighting the heat and did something else entirely. They arranged a relay race. The stopping sequence begins while the station is still nowhere in view. On the Tokaido line, the driver, working to a braking pattern the signaling system enforces, starts shedding speed several miles out. And the first runner in the relay does something that sounds backwards the first time you hear it. The train's own traction motors are turned around and asked to work in the opposite direction. Here is why that is possible. Almost every axle on a modern Shinkansen has a motor on it. On an N700 set, 14 of the 16 cars are powered, 56 traction motors in total, and together they can pour out something in the region of 17,000 kilowatts, roughly 23,000 horsepower. Under acceleration, those motors pull current down from the overhead line, a 25,000-volt supply running at 60 Hz, and convert it into rotation. When it is time to slow, the entire relationship inverts. The wheels, still turning hard because the train is still carrying all that momentum, now drive the motors rather than the other way round. A motor spun by an outside force stops consuming electricity and starts manufacturing it. The moving train becomes a moving power station. This is only possible because of an architectural decision made decades ago. A conventional train hangs its carriages behind a locomotive, and a locomotive can only regenerate using its own handful of axles, while the dead weight behind it keeps pushing. A Shinkansen distributes its motors along the entire length of the formation. That choice was originally about traction, about spreading power across many axles so that no single wheel had to grip too hard. But it handed the designers something they had not been chasing, which is a train that can brake itself with almost every axle it owns. The current it makes travels up through the folding arm on the carriage roof, into the wire the train was drinking from seconds earlier, and out across the network. And this is the detail that tends to stop people mid-sentence. Right now, on the corridor linking Tokyo with Osaka, a service breaking down into Nagoya is feeding current into the very same span of wire that a different train is drawing on as it pulls away from Kyoto. One train's deceleration is physically pushing another train forward at that moment, on that wire. The energy never becomes waste heat. It changes owners. Across the fleet, that recovery trims measurable percentage points off the total electricity the line consumes, which is why operators keep investing in it rather than treating it as a curiosity. This stage is where the vast majority of the speed goes. No glowing metal, nothing grinding against anything else. Just forward motion being quietly converted into a commodity the grid can immediately resell. But the relay runner has a limit, and it is a hard one. The system only produces retarding force for as long as the wheels are spinning quickly enough for the motors to generate usefully. As the train slows, the output falls away. Below roughly 60 miles per hour, the motors are simply not spinning quickly enough. The generated current thins out, and the retarding force fades with it. The train has lost most of its speed and none of its remaining problem. So the train keeps rolling. Pads remain unusable at this speed on a machine of this mass. What takes over? What takes over is a technology that removes energy from 1.5 million pounds of steel while remaining physically separate from it. 30 seconds and it will make sense. This one operates across an air gap, and it is the part that genuinely reads as though somebody made it up. Powerful electromagnets are carried under the vehicle, aimed downward. When a magnetic field sweeps past a piece of conductive metal, it stirs circular currents into life inside that metal. They swirl. They loop back on themselves. Nobody can see them because they exist entirely within solid steel. Picture trailing a hand slowly through a tray of fine sand and the grains curling outward into spirals behind it. Now imagine those spirals forming inside the metal itself, made of moving electric charge instead of sand. Those induced currents do something specific. Each swirl builds a magnetic field of its own, and the direction of that field is not random. It always sets itself in opposition to the field that created it. Nature, in effect, resents being disturbed and pushes back. So the rail shoves back at the magnets overhead, The magnets shove down in return, and that mutual refusal is what slows the train. Two invisible fields leaning into each other across an air gap, with no physical contact anywhere in the chain. The French physicist Foucault described the effect in the 1850s, long before anyone imagined a use like this, which is why the French still call the technology the Foucault current brake to this day. There is a cost, though, and it is worth stating plainly. Those swirling currents do not vanish politely. They warm the metal they were induced in, which on the linear version means the running rail itself absorbs the heat rather than the train. That is a genuine engineering headache, because rail temperature affects how the track behaves, and the equipment needed to generate fields that strong is heavy. A single installation can add close to a ton to the vehicle carrying it. Every kilogram of that has to be hauled up to speed again on the next departure. The consequences of contactless operation are enormous. Nothing wears out because nothing rubs. There is no dust, no squeal, no burning smell. And crucially, weather cannot interfere. Rain on the railhead, a film of ice, snow blowing down off the Japanese Alps in January, none of it alters the outcome by any meaningful margin, because there is no contact patch for contamination to spoil. The force lives inside the interaction between two magnetic fields, and a snowflake has no way to reach in there. The nearest everyday version is walking out into chest-deep water. Nothing grips your legs. The resistance is simply there, and it scales with how fast you try to move. The idea was proven so thoroughly that European regulators took notice. The technical standards written for trans-European high-speed lines recommend that new construction be built to permit eddy current braking, and the German IC3 became the first train in scheduled commercial service to rely on the linear version of it. And that brings us to the hardware you thought this whole story was about. By the time the field-based stage has done what it can, the train sits under 40 miles an hour. The platform canopy is visible through the cab windscreen. Passengers are pulling bags down from the racks. Only now do the friction pads engage. Examine the task they have actually been handed, though, because it is not the one you assumed. They are not arresting a machine traveling at close to 200 miles an hour. They are taking a train already moving at something near jogging pace and setting it down gently on a painted mark on the platform surface. That is a completely different engineering problem, and it is one that Friction is genuinely excellent at. Pads are precise, they are predictable, and at low speed, the heat they make is trivial. Used at the right moment, they are the correct tool. Used at the wrong moment, they are a disaster. Nothing about the material changed. Only the timing did. There is also a quiet reason the platform stops look so effortless. On many services, the final approach is not being judged by eye at all. An automatic stop control function takes over near the platform, comparing measured distance against a stored profile of the station and trimming the braking effort continuously until the train settles. The human in the cab supervises rather than steers, which leaves the fourth technology, the one that has been running silently underneath everything you have heard so far. None of those three systems decides anything on its own. Sitting above all of them is a control layer that never appears in the photographs. Onboard computers read the train's exact velocity, its loaded weight, the distance still to run, the gradient and curvature of the track ahead, and they do this many times per second. From that, they calculate how much retarding force is required at this instant, then divide it between motors, magnets, and pads, adjusting each individual bogie separately so that no wheel is asked to do more than it can hold without slipping. The handovers you have been following are not three switches thrown by a driver. They are a continuous blend, managed by software, in which one system's contribution decays as another's rises so smoothly that nobody in the seats can feel the changeover happen. The proof is the stop itself. A Shinkansen is expected to halt with its doors inside about 20 inches of their marked positions on the platform, which is what allows the Q markings painted on the ground to mean anything at all. Not usually. Not on a good day. Every arrival, thousands of times daily, across a network carrying hundreds of thousands of people. And that precision is not a party trick. It is what makes an 8-minute turnaround possible, and the turnaround is what makes the timetable possible. And now the twist that reframes all four. In a genuine emergency, the most sophisticated part of that chain is deliberately abandoned. Regenerative braking depends on the overhead wire being live, because the electricity the motors produce has to have somewhere to go. In a serious earthquake, the first thing that happens is the power dies. So Shinkansen emergency braking does not lean on regeneration at all. It falls back to the friction discs, the crude, heavy, heat-limited component you were told at the start was almost useless. It is the only element in the entire architecture that needs nothing from the outside world. That is not an oversight. It is a design philosophy. Elegance handles the ordinary day. The blunt instrument is kept for the day that goes wrong. The newest trains push that logic further. The N700S, in service since 2020, carries lithium-ion batteries beneath several of its cars, built around silicon carbide power electronics, light enough and small enough to make the installation possible in the first place. If the catenary goes dead in a tunnel or on a viaduct, the train can move itself, slowly, on stored power, to somewhere passengers can safely get off, without any wire above it at all. Even the four-system architecture is not fixed. Older Shinkansen generations carried eddy current brakes specifically on their unpowered trailer cars, since those cars had no motors to regenerate with. When the N700 arrived with 14 of its 16 cars motored, the design team dropped the eddy current hardware entirely. Regeneration now covered enough of the train that the extra weight, close to a ton of magnets, was no longer worth carrying. The relay was rewritten as the fleet changed. And this whole principle is already in your life, whether or not you have noticed it. Ease your foot off the pedal in an electric or hybrid vehicle and watch the small dashboard gauge tick back toward full. That is the identical conversion, scaled down. Motor spun backwards by the wheels, leftover speed banked as charge instead of thrown away as warmth in the brake discs. Take a lift down from the upper floors of a recently built tower, and the motor overhead is often feeding a trickle of current back into the supply that serves the rest of the building while you descend. The journey partly pays for itself. Brake an electric bicycle on a long downhill and see the battery percentage climb. What you are holding, at a scale small enough to lift, is the bullet train's main deceleration system. Same physics, same conversion, same refusal to waste. So when that train slides into the platform and the doors settle onto their painted marks without the driver touching a thing, you are not watching brakes work. You are watching the result of engineers accepting that certain physical limits cannot be beaten and choosing to navigate around them rather than through them. 4 technologies, each assigned the narrow speed band where it outperforms the others, each passing the problem along at exactly the right moment. All of it orchestrated by a computer that finishes the entire sequence before most passengers have looked up from their books. The next time an electric vehicle slows without anyone touching the pedal, remember what you are sitting inside. The same idea that takes a train from nearly 200 miles an hour down to a stop, measured in inches. That the intelligent response to unwanted energy is never to annihilate it, but to route it towards something that can still make use of it. If some ordinary object you pass on your way to work has ever made you quietly curious, leave it below. All of them get read, and the strongest ones become episodes. Subscribe, and the next one will find you.